Good morning. As Tunda's colleague, I'm honored to host today's morning session, which consists of two workshops. And the first workshop will be given by Professor Joseph Hall on systems factorial technology with R, and second talk by Professor Daniel Little. As we all know, the importance of science is learning by doing. So being able to learn to really get our hands dirty with this famous technology will be very cool. But I was also notified this morning that unless you have downloaded the packages earlier, or the network here is a little bit problematic today, so either we have to take notes, work hard on our notes, and then learn afterwards. Just stay concentrated to the talk. So that aside, let's all welcome the first speaker, Professor Joseph Hall.
Thank you very much, and thank you again, Professor Young, for hosting the conference, and to the community here for having us out. It's a huge honor, and we're very excited to be able to talk about our work in this environment. So thank you. I'm going to be talking about, I'm going to start by giving a general introduction to systems factorial technology. If you were here yesterday, you got to see Mario Pivich and Dan Little talk some about particular aspects of the framework. So I'll kind of review that information and give it a kind of more global context of understanding cognitive models or cognitive processing. And then I'll dig in more into the particulars of using the R package that I've developed with some colleagues to do these analyses. Okay, so starting off then, what exactly is systems factorial technology? The basic idea is that we want to look at how people use multiple sources of information in cognitive or perceptual processing. And those multiple sources of information can be a wide, diverse range of things. So the example that we'll be focusing on a lot is this simple two-dot task. The task might be just detect if there's a dot on the screen. One source of information could be considered this top dot. The other source of information could be the bottom dot. I can flash either one on the screen. Be lights and sounds together, so different modal information from different modalities. They don't necessarily have to be anything that we would really consider a perceptual cognitive feature. So the top half or bottom half of the face can be used in this technology with the two different sources of information. Or in this case here, we've got information from two different sensors, like a visible sensor and a heat sensor, that we can look at how the sources are combined, whether using technology or how the cognitive system might combine sources of information. So it's a very general framework for addressing this question, how different sources of information combine together. And to tackle this question, we're going to divide it up into a few different aspects or properties. The first question we ask is, are the different sources used concurrently or one at a time? So this is this question, serial processing or parallel processing or coactive processing. The second question we ask is, how many sources are enough to respond? So is it enough to identify a face to just see the top half of the face, or do we tend to always deal with the whole face before we make any response based on that information? Does knowledge of one source of information affect how we process the other source of information? So does the degree to which we've detected that top dot in the two-dot situation affect at all how we perceive the bottom dot, for example? And then finally, can we dedicate the same amount of resources to processing each source when we're dealing with sources of information in isolation or in the context of more sources? So if we're doing a task and we only have to deal with visual information, are we then slowed down if we also have to attend to audio information? Okay, so those are generally the four questions. This question of, the first question we call the question of architecture. So in case there are any people who are ACTAR modelers in the room, this is totally distinct than what somebody in the ACTAR framework would call as architecture. By this we mean really distinguishing between parallel processing, where full source of information are processed at the same time, or serial processing, where it's one source of information at a time. And then this third case that's come up a lot, particularly with respect to configural perception, is coactive case, where there isn't really a distinct treatment of the two separate sources of information. The information is pooled and then used as sort of one single part. The next question we call stopping rule. So this is how much information is required to stop. So we distinguish then between an and stopping rule that can be combined with parallel or serial, meaning you have to wait for all of the information before you respond, or an or stopping rule, where sometimes referred to as self-terminating, where as soon as we've dealt with one source of information, that's enough to make a response. The next question we codify is stochastic dependence. So this is that question of how much the perception of one source of information affects our perception of the other source of information. And here we use this concept from probability theory, stochastic independence. So does the time it takes you to deal with one source of information and the other source of information, can you split that up into the product of the two distributions? So this is just the definition of independence from probability theory. These two events are independent. You can write the joint with the product of the margin. So we take our ideas about the time it takes to process information and just drop that into the definition of independence. Alternatively, there could be some reason to have a violation of that independence. So where information is perhaps shared in the process of perception. For example, in our face perception, we probably share information from the top half of the face and our perception of the bottom half of the face. We're not truly independently splitting it up for the top and bottom half of the face. This next question we refer to as workload capacity. So this is how the different processes change as we add more and more information that you need to deal with. So we usually divide this up into kind of three classes. One is limited capacity, where if you're dealing with one source of information and you're extended to two sources of information, you have somehow less available processing resources with two than you do with one. So there's some limitation as you increase the source of information. The next we refer to as unlimited capacity. And no matter how many sources of information you're dealing with, you can dedicate the same amount of resources to them. In contrast, then the final one would be supercapacity. So the more things you have to deal with, the better you are at each individual thing. So if you're just dealing with, this is a nice special case when we're looking at configural perception. So it may be that when I'm dealing with just, say, the bottom half of the face, I'm not attending to it that much, but once I have the naturalistic image of a whole face, it actually gets more of my attention. I'm better at perceiving that whole face, including the bottom half of the face in the context of the face. Okay. So just to review, we've got these four concepts that are answering these questions about how sources of information are processed together. Architecture, particularly serial, parallel, and coactive. Stopping rule, first terminating or exhaustive, and that could be paired with either parallel or serial. Workload capacity, how the information resources change as you add more sources. And then the stochastic dependence, whether the sources of information are processed independently or have some dependence in the process. All right, so that's a very quick and dirty overview of systems factorial technology. There's a huge background of literature in developing these concepts. I'm happy to answer questions afterwards about the right places to read, the right person to talk to. Of course, in the room, Jim Townsend, who's developed a lot of these methodologies. And again, I'm happy once I started to dig into the nitty-gritty to go back and review into this stuff. So once I get into the nitty-gritty, interrupt me, raise hands, shout at me, whatever you'd like. So I can be sure that you're following along with these concepts. All right. So that's the overview of the theory. You got a dose of that yesterday. Some of these measures that I'll talk about will be familiar from Dan and Mario's talks yesterday as well. And this is where I'll also get into the R code. So not just showing you what the measures are, but showing you how you would use R in our package to calculate these things. Okay. So the first measure I'll talk about is the workload capacity coefficient. And the idea is this, is it indicates changes in processing of parts as you increase the workload. So to measure this, we're going to first fix a baseline of performance, which we call the USIT model. And this stands for unlimited capacity. So our baseline model assumes there's no change in resources available or performance on each individual part as you increase the number of parts. Independence, so we're assuming the two sources of information are independently processed with no effect one on the other. And parallel. So we use these three assumptions together to fix a baseline of performance, and then we compare true human performance to that to get an idea better than the baseline, worse than the baseline, or roughly equal to the baseline. Okay, so then the measure itself, we have a different measure for different stopping rules. So the baseline for the or stopping rule or first terminating processing rule, you basically want to take these three assumptions and encode it in the model. The first step in a parallel OR process for you to have stopped, so say I tell you if either of those dots show up on the screen, say yes. For you to have successfully, if you haven't said yes yet, it means you either haven't detected the upper dot or you haven't detected the lower dot. So if I show you both dots, but you haven't responded yet, it means you haven't seen either of them, right? Because as soon as you see either, you can say yes and stuff. Good? And so here, this is the time for both the upper and lower dot. This is the time for the upper dot in the context of the lower dot, and the time for the lower dot in the context of the upper dot. Now, using these assumptions of independence and unlimited capacity, we can just drop this in the context of. We're basically saying, I'm going to estimate what's going on here by ignoring the fact that it's in this context and saying it's the same no matter what. And that comes from these assumptions. All right, and then using this independence assumption, I can split this joint of this time and this time up into the product of the probabilities, right? That's coming straight out of that definition from earlier. So this is, I'm using this term S here, the survivor function. So this is just a rewriting of exactly this probability. S A B of t is the probability that this time is greater than some fixed time. So just change of notation here. To get the capacity coefficient measure, we change these into the cumulative hazard functions, which in this case, you just take the logarithm of both sides. So the negative log of the survivor function is the cumulative hazard function. We take this log, the negatives drop out. We get this capital H, which I refer to as which is the cumulative hazard function. So what this then does is this gives us a baseline of performance with both parts, both parts together in relation to each of the parts individually. So the baseline processing of unlimited capacity independent parallel says that when you're dealing with both dots together, it's the sum of these cumulative hazard functions when you come the top dot alone and the bottom dot alone. You can go through the same steps for an exhaustive rule. There's also this newly developed measure for single target self-terminating. So that might be, you've got a target either alone or a target in the field of detractors. So your response time always just depends on how long it takes to deal with the target. But you may be slowed down by the context of distractors. And then also, I don't have this built into the package yet, but the resilience functions that Dan was talking about follow very similar logic. So that's future work is to include that in the package as well. Okay, so these are the basic ideas of the measures. You can also come up with different variations on this for different stopping rules. So if you have an exclusive OR, for instance, follow the same steps and get a very similar measure. Okay, in terms of actually estimating these functions. So to estimate the cumulative hazard function, the most efficient estimator here is called the empirical cumulative distribution function. The basic idea is you take this function YAB, which is the number of response times that haven't happened yet. This is sort of like a survivor function. And then you add that fraction up for every time that has happened so far. Looks a little messy. It's even messier to explain. There's a not exactly easy to read paper that I've got out on using these measures, using these estimates for the capacity coefficient. The nice part about this stuff is that it's all under the hood in the R package. So as long as you can get your data in right, it's probably good that you have a rough understanding of what it's doing here. But the R package is going to do the heavy lifting for you. But just to show it up here, basically we've got these nice estimators here that have all the nice statistical properties. They're unbiased and long run, converge to the truth, things like that. And we also have variants of those estimators. So now that we've got our estimator and our variance of the estimator, we can actually turn that into a z-score. And that z-score then can be used for hypothesis testing with the capacity coefficient. So pictorial, a little bit of detail on what's going on with the z-score. The basic idea is you've got hazard functions, which would be the derivative of the cumulative hazard function. For your two sources together, you add those up to get your baseline performance of the USIT model. And then you take your truth performance and compare it to the USIT model. Now these statistics allow for the use of a weighting function, so you can weight different areas of the response time scale differentially to compare against this null hypothesis of USIT processing and true group processing, how people actually perform when they have two dots on the screen. And again, that's all kind of under the hood, but the math is worked out and you can do it officially. Okay. So I'll pull up R in just a moment here, but generally you want to use capacity coefficient because it's going to provide a yardstick. So it gives you a scale of measurement before processing two sources of information. And this is normalized by how long it takes you to process each part. So because we're using that USIT model as a baseline, we're using the information about each part to get us the baseline of performance. That way then we can compare it across things that may be disparate. So we can, if we have, say, two faces and the bottom half I use is different from the top of the, in one condition and another condition, I can compare across those two conditions because I've used that baseline to accommodate for the fact that we have different pieces. It is a response time-based measure, so it's more sensitive to a lot of model characteristics and accuracy. I'll get back to building accuracy in later. And then also it's a dynamic measure, so the value of this capacity coefficient can change across time. So there's a lot of information available. Okay, R code. We switch over to the R program rather than just showing R code up here, so I can step you through it. Is that text size all right for everybody? In the back? No? Cool. All right. So first thing is this package is available on CRAN. So as you would normally install any R package, you can do the install.packages, or if you're in RStudio, you can bring up the package manager. It's called SFT lowercase. So once it's loaded into your system, again, like any other package, just library SFT to load it into your workspace. We've made an effort to document this program at least reasonably well. And then in places where more details might be necessary, we've got the links to the relevant papers. So for instance, if I wanted to know about doing the OR capacity coefficient, if I could spell correctly, we've got the help page in here. It breaks down the use of the command, so it's capacity OR, what you need to input, so it can take in both the response times and the correct information. So as a side note, it uses this correct information to modify the response time distribution based on censoring. I won't go into any more details right now about it, unless you want to ask me questions later on about what I mean by censoring and how that affects the estimate. But if you want, you can just ignore that and only put in correct response times. So the basic idea for this is you have a list of the response times array, where the first array in the list is assumed to be the exhaustive condition. So if I had my data for my two dots task, my first item in the list would be all of my response times for when I showed the participant both dots. The second in the list would be response times when I only show the participant the top dot. And then the third item on the list would be for when I show the participant only the bottom dot. And then if I have these corrects, just indicators, one's for correct, zero is incorrect, I can add that in and they just match up. So the first on the list would be correct or incorrect indicators for the two dot condition, or the two dot tries. Okay, so this has some of the details that I kind of went over in the slides about what exactly the capacity coefficient for the ore is. This idea of super and limited capacity and unlimited capacity. Okay. And then the output. So we get the CT. This is a step function class object that represents the capacity coefficient function across time. So this can be useful for plotting, or if you want to calculate the value of a particular time step, you can use that for the output. The var. So I showed you the ratio version of the capacity coefficient. The statistical test is actually based on the difference between the two target and the sum of the individual targets. So if you want to return the distance function, it will also return the variance of that function, sorry, the difference function. And then this last one, this C-test, is that hypothesis test, that null hypothesis test of unlimited capacity independent parallel processing it returns. And this is returned as a hypothesis test object in R. So it has what your p-value is, what the statistic is, and some basic information like that. So I'll go ahead and just copy and paste this example from the documentation. All right, the basic idea, I'm just going to generate some response times for the individual target conditions. So right now I'm just using exponentials, so I randomly sample 100 exponential response times with rate 1 and with rate 2. So that might be your rate of processing the top dot and your rate of processing the bottom dot. They don't have to be the same, they're different here, but perhaps in reality it's not too different to detect the dot above fixation, below fixation. Either way, for simulation purposes, we've got them set to different. Okay. And then here, so if I wanted to have a limited capacity system and simulate that performance. So the parallel OR system means that we're taking the minimum of response times to the top and to the bottom. So I'm going to take the minimum of things I would generate with respect to the top and to the bottom. And to make it limited capacity, I'm saying, well, when I've got the top dot in isolation, it's just this rate 1. But now that I have it in the context of the other dot, the rate is half as much. And I do that to both dots. So this limited is simulating that idea. We have the two of each other, the rates slow down for your exponential process. Unlimited, I just leave the rates alone. So these responses that I've generated for the bottom dot are samples from the exact same distribution as when I do it alone. And then for the supercapacity condition, now that they're in context, the rate is twice as high. Does that make sense in terms of the simulation? Good? Okay. All right. The first thing that I did run is I used this capacity OR function. I've got my response time list here. So it's RTPP limited. That's my list of limited response times that I generated for the 2-dot condition. My RTPA, so PA is for present absent, that would be the top dot only, and then AP, the bottom dot only. So I've got that in my cap dot limited. So I can look at the value of the hypothesis test here. So it tells you what test you ran, what data you input, the z-score from that that we derive using those measures. So the z-score is minus 6.15. Hopefully you're mostly familiar with z-scores, that's pretty low. And indeed the p-value that you get related to that is 7 to the minus 10, or 7 times 10 to the minus 10. Right, and then also in R, it's, with these hypothesis testing objects, you can say what the alternative hypothesis is. So the null hypothesis is that the performance in the 2-dot condition is exactly what you would expect from a USIT model. And we reject that null hypothesis based on this very small p-value. So then we would have evidence in favor of this alternative hypothesis that response times are different than those predicted by that baseline usage model. Yeah.
Can you plot how does the function look like in the capacity function?
Yep. Yeah. So the other object that's returned as part of this output is the step function object. So let's see. If I want to look at between, I don't know what the rate of scale is. So this is just calculating the unlimited and supercapacity ones as well. I'm going to put them all up on the same plot. You don't need to, but it's possible. Okay. So, well, let me start by just doing the or one. All right, so if I wanted to plot for that first one, the limited test, I take my t-vec, which is just a vector of times. Those would be your, whatever your response times are in your condition. So I plot that would be the output of that one. So this is sort of a basic plot. You probably want to jazz it up a bit before putting it in a publication. But basically, we've got this capacity function across time, and it's showing me the value of that estimated capacity function for each of the input t-vec. The nice thing about using the step function object is you actually don't even need to put in the t-vec, I don't think. Sometimes it fails, because R likes to mess with me. Try it out. So I didn't necessarily need to specify what t-vec values to put in a step function object. It's just assume we put something in. Okay, so just recall from the capacity coefficient that the baseline of processing predicts that it's going to be equal to 1 across all time. And as we expected from simulating these to be fairly limited capacity, this function stays well below 1. So at the top of my axis here, I've got 0.5. It never even gets up to 0.5. The true value direction should be 0.5, so by sampling we've ended up a little below, but the basic idea is that this is fairly limited.
Shouldn't you have, is there any bias in these estimators such that, unbiased, but that one in particular looked like it was estimating a little lower than the true population value. Can you make a general statement about whether it's a number or overestimate?
So the individual cumulative hazard estimates are unbiased estimators. So it was a little bit low, and that was probably just due to the particular sample of times we used. So if we took 10 times as many samples, it would be much closer to the true value of 0.5. There's a caveat that when we're looking at this, looking at the difference of these functions, or the ratio of these functions, that the limit as time goes to 0 isn't 0 of the estimator. So there's bias in the very far left-hand tail as you go down here, or in the end function of the right-hand tail. So I can't remember how it looks with the example data I have from the dot stats, but sometimes when you look at real data, you'll see that even if it's limited, it'll kind of jump up to 2 or something as you go farther to the left. The hypothesis test, so your variance in these estimators gets really wide when you look at these ratios on both ends. And so because you're using the variance in that z-score, it basically is ignoring that part of the distribution for the hypothesis test. One thing sometimes I'll do is I'll just take I'll take a range where the variance is low, kind of in the middle of this function, and only plot that to have really a better visual representation of where we are correctly estimating the tax.
Well, one interesting thing is very, very often we get the supercapacity. We get that the supercapacity does tend to show up earliest in the RTs and then go down like that. And I see that right there, and I'm wondering if, because in principle, that should be sitting flat at 2. For your example.
Yeah. So again, if I increase the number of samples, this would stay up at 2 longer. So I think, as the variability gets high here, whether this is down here or up there, depends on very few sample response times, especially in an exponential, where you're just sampling things that are kind of far out here, you don't have to do it anyway. I think probably the reason that in general in data we would see it kind of taper off down here kind of has to do with that long tail that we generally see in response time distributions as well. So again, that's an advantage of looking at the variance of these estimators, so that we're not even plotting that part. It's not really meaningful, but not as meaningful as the part of the data where we have good estimators. Okay, I'm going to move on from capacity because I've eaten up a lot of my time. Okay. Jim and Ami in 2011 had this nice paper where they connected the capacity coefficient with some other bounds on processing 2 sources of information. So the race model inequality is a fairly famous one that's here, and they developed what that would look like if you were looking at those bounds, but on a capacity plot. So rather than just looking at CDFs of response times, what those bounds would look, what that upper bound, lower bound, depending on how you're looking at it, what that bound would look like on a capacity plot. So we've also got those bounds built into the R package. So if you're interested not just in the capacity coefficient, but also whether your data show a violation of the race model bound, or these other bounds have been developed, this one based on some Price's work by Polonius and Forberg, what those bounds look like with respect to capacity. So I'm not going to run this code now. I'll leave it up here for just a second to walk through it. Same idea, simulates and performance. This is an OR task here. An AND task would be the max of the 2 response times for the model. And we just use this estimate bound. So again, this RT is just the same kind of list. Kind of use different nomenclature for the pieces here, but your list of response times for each of those. Again, you can have correct or incorrect in here, so we can use those in the estimators. This assume ID is we assume identically distributed. So if I'm assuming that the top and bottom dot have the same response time, I can just have this one in here and assume identically distributed. And then unified space, this says whether we're plotting this in, if unified space is false, we just see these CDF bounds. So this would be the kind of plot you'd see in papers where they use the race model inequality. Where you see your actual performance, and then you've got an upper bound given by the race model inequality, and a lower bound given by the Price bound. If you put unified space equals true, it's going to give you this plot in capacity space. So based on that work by Jim and Allen. Okay, so now just to give you some example, using this with real response time data, got that dot task I was talking about. The main thing we're going to focus on for capacity is comparing what happens when you've got just 1 dot to what happens with 2 dots. So just the upper, just the lower, comparing to 2. So these data from this task are actually included in the package. So if you want to play around with data before messing around with your own data, it's just this data dots to load it. I've got this data in a particular format. If you're using a lot of the functions in here, you can have your data in whatever format you want. there's some convenience function that we'll go through and calculate capacity functions and SIC functions for everybody in your sample. If you want to use those convenience functions, you have to use kind of a particular coding scheme for your data. So the way these data are set up, we've got a subject column, a condition column. So this condition or means that they could respond if they saw either the top dot or the bottom dot. These data also include an and condition. We told them you can only respond yes if both dots are on the screen. Response time, so this is a single trial, so participate in the or condition on this trial at 289 milliseconds response time. They were correct, so 1 is indicating correct, 0 is indicating incorrect. And then each of these, I'll come back to over the SIC, but if you remember from Mario's talk, we've got the high 6 condition, so high salience on both of them. So the 2 indicates high salience. 0 would indicate absent. So if I, for instance, wanted to encode having the top dot at high salience and the bottom dot not on the screen, I would encode that in these data as 2, 0. There's also capability with these to have distractors in there. So if I had a high salience distractor, that would be a -2. So that's the general coding for the data. You can look, there aren't distractors in this particular version of the dots task. So looking at the full data set, you're not going to see negatives there. It's just 0s, 1s, and 2s. Okay. So then, let's see. So this capacity group function, I can just run that, and it's going to tell me for all of my participants and all the conditions that are in there. In this case, I've just used the OR condition. I want to look at the capacity coefficient. So I can specify which stopping rules, so which baseline performance I want to use. So right now we've got the or and the and the STST, so those 3 rules that I showed you up there to give you the baseline of performance. Let's see. So it runs through and it'll show me the capacity function for each participant. So it'll run through, and then it also gives me this plot that shows all of them. Again, these probably aren't plots you'd want to just drop in a paper, but they're nice in your analysis to kind of get an idea of what's going on in the data. So notice that in these data, for the most part, well, everybody is down here below the baseline of 1. So for those 2 dots on the screen in the OR task, everybody's limited capacity when we look at it visually. You can also get a summary of what the statistical test came up with. So for each subject, statistical test, it'll say limited here if it was significantly different than the baseline condition, and negative, so worse than baseline and significant. So every participant was in fact significantly limited using the test. And then this here just gives you a summary of the groups of the t-test for the group. So the group level was limited as well. I can also, if I want to access individual capacity functions here, so this for the second participant. This object is that step function object, so if I want to plot that individual's capacity function, I can grab that. It also has the output of that capacity test. So that's all included when you run this group level. So it can be kind of a pain to build everything into that exact format, but once you use it, it does these group analyses very quickly. Okay. So that's what the data look like for the OR and the AND capacities. They're in there. So if you mess around with that data on your computer, make sure you're using it right. It looks like this. Okay. I'm going to go pretty quickly through this. the capacity function, we've got this data that functions across time. When you use a statistic, like the z-score statistic, it's basically integrating all of the function across time. So we lose out on all the additional information we get by having a function. One way to deal with that is still extract the information of the whole function is using what's called functional principal components analysis. So if you're familiar with standard principal components analysis, the idea is you've got some vector in a high-dimensional space. For each of your data are vector in a high-dimensional space. You want to project it on some lower-dimensional space and try and describe the data on the lower-dimensional space. So it's the same idea with the functions, but instead of talking about vectors, we're using functions. Think of it as infinite dimensional vectors, if you want. Great paper with Kevin Burns as the lead author on it that describes all this stuff in detail. All I want to say is it's built into the R package as well, and fairly easy to use. So, again, if you've got, like this is the built-in dot state, if you've got it in the right format, you just say, do this capacity FPCA stuff with my dots data, dimensions to plot the principal components is true. So this comes up with principal component functions, basically, that describe variability around the average of all the capacity functions in your data set. So this just shows what the mean is, and then the mean plus some multiple of the component functions, and so on. So this first component represents a general positive increase over the average. And then the second component really is focused on increasing the tails. There's also, in this case, there's just a representation of, across the different conditions, what the different scores are. So basically the loading values for these principal components. So I think the axis is flipped here, but the idea is that the OR task and the AND task have very different capacity functions. When using the OR capacity coefficient, this must be the AND capacity coefficient here. So the OR tends to have much higher values here. It's much higher up in the capacity function. So if we put people in an OR task and compare them to an AND baseline, they're going to be better at higher functions. And we can also see individual differences here, which is really nice. So in particular, this participant 5 really didn't show a lot of difference in either of these component functions between their OR and AND capacity functions. Everybody else showed big differences between the two of them. So we want to know what's going on with subject 5. Okay, that's the functional principal components analysis. Assessment functions, so the capacity functions are basically only concerned with correct response times. We use that censoring a bit to get better estimates of the correct response time distribution. But the assessment functions that were developed by Jim and Nick Altieri, and then updated with Chris Duncan, Dan Little, and myself, to include sort of another condition, account for accuracy in comparison to the baseline as well. So we still have that USIT baseline, we just extend that baseline to making accuracy predictions as well. And to compare actual performance to the accuracy as well. And there are a number of different variations on this function. So you can have functions that focus on the CDFs and correct response times. So you refer to those as the correct and fast. And then you can have different baselines of processing and or in principle you could do it with STST or XOR as well. And then there's also a difference between detection and discrimination. So the DOTS task is a detection task. You can have another task where if you've got distractors, it would be maybe a discrimination task. So you can specify detection or discrimination. You might have slightly different baseline models for each of those. Okay, so those are the functions. This is actually the shortest function. The page in the paper where they list all of them is just a page of integrals. So it gets pretty complex. So it's all in the R package. So it's good to kind of read through the paper to understand what you're doing. But rather than trying to hand code up all the things that are going on in the integrals, it's all here in the R package. Again, I'm not going to run this because I'm a little low on time. But we're just generating response times again. You combine them, say if it's an OR task, you combine the minimum time rule. We're separating out correct and incorrect response times. And so we can use these assessment functions. We can do a correct and fast assessment function for detection. Correct and fast just means it's CDF. correct and fast is false, means it's based on the survivor function. One wants to see that. Incorrect and fast, incorrect and slow. So depending on which version of the assessment functions you want, you can just set these flags in here. We'll run the code just to show you the pictures, but not step through it. Right. So if you notice in the example, I've got 1,000 trials per distribution, or sorry, 1,000 trials that I'm sampling in there. Maybe 10,000, 100,000, a lot in there. So when the generating model is actually the baseline with that many samples, we get these nice functions that are right across the line for all of them, correcting fast, correcting slow, and correcting fast and correcting slow. So the generating model is the baseline model. It does come out with the baseline model on all of these measures. Okay. So that's the capacity. That's only about half of the information. The other thing is the survivor interaction contrast. So this is the content that Mario was talking about. This is really nice for distinguishing among different processing architectures. So again, distinguishing among parallel and serial, as well as distinguishing stopping rules. So again, we've got these different conditions where we manipulate the salience of items. So if you're detecting the dots, it's easy to detect when it's high contrast, harder to detect on low contrast. When we factorially combine high and low contrast, along with the presence and absence of each of those dots. So there's that picture I showed you before. Mean interaction contrast gives you some identifiability in these models. It's there, it's in the program, I won't talk about that anymore. Survivor interaction contrast takes the survivor functions of the response time distributions for each of those four double present conditions. So when both are highly perceivable, one is low and one's high, and then both are low contrast for the dots. We just take the interaction contrast. So what is the difference in response times when we fix the first dot low contrast and change the second dot from low to high? Compare that with the fixing the first dot to high and going from low to high in the second. So the same kind of interaction contrast we look at, say, for an ANOVA, looking for an interaction of 2x2 ANOVA. Now we're looking at survivor functions, and we're particularly concerned with these high and low salience conditions. So for each of these models, parallel exhaustive, serial exhaustive, parallel OR, and serial OR, and coactive, we get distinct shapes in the survivor functions predicted. All right, so then because I'm particularly concerned with statistical testing, we want to convert these predictions models into hypothesis tests for your data. And to do that, we basically are generalizing the Mordorov-Smirnov test for cumulative distribution functions, which looks at the maximum difference between two CDFs. We generalize that to the maximum double difference, or the maximum SIC. And we do one side as the maximum positive and maximum negative. There's some math that's built into the package, and can give us hypothesis tests. We can then use those hypothesis tests to get an idea for what potential models might have generated our data. So for instance, if the positive part and negative part are not significantly different from 0, that's something that will be predicted by a serial OR model. If only the positive part is significant, but the negative part is not, that's something predicted by the parallel OR model. Coactive model predicts, picture's not here, but significant positive and negative parts, as well as a significant mean interaction contrast to distinguish from the serial M model, positive and negative are significant, MIC is predicted to be 0. So with each of these models, we predict this pattern of data. You can't exactly go backwards here because it's hypothesis testing, but you can be close to backwards if you've got good power in the data. Okay, so this is what it looks like in the R package. Got 20 minutes to 10, 20 is the final time. Shut up by then. All right, well, I'll run the example through to the picture. The basic idea, again, we're generating response time distributions from the exponential. We've got our channel 1 high, I'm saying is rate 0.2. Our channel 1 low is something lower than that, so the rate 0.1. And then channel 2, I've got slightly different rates, but high and low still. And the high response time for parallel OR would be the minimum time of each of those. High-low would be the minimum of the high and the low, etc. And then to calculate the SIC, we've got this SIC function where we just need to specify what the high-high is, the high-low is, the low-high, and the low-low. So I dump that in there, I get this parallel lower SIC. I'll jump over and show you what that output looks like. So again, we get a step function object, it plots the SIC across time so we can look at it. The parallel or the generated data is all positive, as we'd expect. We also get another hypothesis testing object that comes out. They actually, a little more complicated once you get out of this. Okay. So this dumps out a lot more information. So we've got a statistical test for the MIC, a test for the negative part of the SIC, and a test for the positive part of the SIC. It looks like for this particular data it wasn't significantly positive or significantly negative, neither the MIC was. So not particularly good data. You probably didn't use enough trials in here. The basic idea, you get each of those tests. So you get the test for the positive part, the negative part, and the SIC or the MIC part. It also does this, so it's got the step function in there just like the capacitor did for plotting. And it also does this series of KS tests for dominance. So one of the assumptions that you have in the SIC is that the high-high is faster than the high-low, in the strong sense of faster, stochastic dominance. You kind of have the ordering you expect. So when both are high salience, it should be faster than when either one of them is low salience. And when at least one of them is high salience, they should be faster than when both of them are low salience. So this goes through and does a series of tests for that. And so you can kind of get a summary of what's going on there.
So is that the reason that it's because you didn't have
I think the reason I have significance is that I didn't use that many times. in there.
right, which could have led to call for failure or something.
Right.
That's not.
Yeah, so these ones should all be significant, and these ones should all be not significant. So notice that these two are not significant here, and potentially that could happen. So this means that there should not a very big difference between high and high-low. So there may not have been enough of an effect there for this not to pick up the significance, and then hence the SIC might not be significant. I ran the simulation a couple more times. I picked the numbers in that example so that in general it does come up as significant. Bad draw on the random roll of dice this time. There's also this SIC group function you can use as well. And just like the capacity group, it gives you an overview so you can see for each participant whether they passed their dominance tests, what was significant, the positive, the negative, and the MIC. It also tells you what particular models could predict that pattern of data and what models are rejected. So what models are clearly rejected by your pattern of data. It gives you a nice overview table of your data. And again, it has a list object that's returned that has the same output you would have from this run for each participant in each condition. This is what the dots data look like for the OR task. I guess I didn't spot the end. So in the OR task with that data that's included, you can do SIC group with dots, the data dots that are in that way format. It gives me a picture of each individual's SIC. The overview table told me that 9 to 10 participants had significant positive values, and the negative was never significant. MIC was also significant for all of them. It's pretty clear that when we tell people to say, press when you see either of the two dots, either or, that they do in fact use an OR stacking rule, and that they're processing the information in parallel. As a note, the AND test, there are actually a lot of violations of selective equivalence. So in the AND test, they look just as pretty, but are all negative, and what we'd expect if they were doing parallel AND. There's a little bit more messiness in the data. So that's all there. No mess with it. Okay. So we've developed a framework for addressing this general question: how do different sources of information combine into the process? The capacity coefficient and the assessment functions. We're seeing how things change when you increase the workload, when you add more sources of information. Survivor interaction contrast for measuring architecture and stopping rules. As a side note, we're going to look at dependence relations for interactions, facilitation, and inhibition. You can sometimes use the two of these together to get a nice idea of what's going on with that. Finally, to acknowledge I've had a lot of help working on this package from Leslie Blaha, the U.S. Air Force Research Laboratory, and Devin Burns, who's now from the University. It's been supported by the Air Force, sorry quite a bit, Dan Richard, Jim, and myself. All right. Done now. I think we've got a fair amount of time left, which I was hoping to have so that you can ask me any questions you want, or if you don't want to ask questions, I can just do all sorts of things with the package. But I'll start with questions. Thank you.
Joe, can you explain more about the functional principle component analysis?
Sure.
Basic presentation.
Yep, absolutely. So, the basic idea here is that we're treating each function as sitting in this high-dimensional function space. But if we only have, say, 20 functions, so a capacity function for each of my 10 participants and or condition and end condition, then the true range of data is only 10 dimensional. We've got, well, 10 dimensions of functions, right? One for each. So if I want to look at the variability across those 10 functions, I don't need to use an infinite dimensional space. So what I want to do then is I take the average function and look at how people are different from that average function. And so in principal components analysis, we take our first component to be the dimension along which the vector varies the most, or your data vary the most. So the same thing, we want to look at the function that represents the most change from the mean function across time. So there's one function that represents that change in the function from the mean across time. It's the most variable. And we get at that by looking at this, basically the L2. So we integrate the function across the time range, different from the mean, right? And we sum those all up, and we want to maximize basically how different it is from that mean function. So this is the exact same procedure as principal components analysis. With principal components analysis, you usually use the eigenvalue decomposition, but it's doing this. We're just using, instead of a vector in here, we've got a function across time in here. So that's kind of theoretically what's happening with those. We also use the Verimax rotation on this. So this is something that usually psychology folks who use PCA tend to use. The idea is once you've got a representation of a lower dimensional representation of your data, you want to rotate that space in such a way that you've got maximum difference in your loading scores, maximum score difference from zero. So you want each of the dimensions to really highlight big differences among each of your data. So in particular,
So do we need to determine how is it how many components?
yes. Yeah, so
And is it orthogonal or?
yeah, it is orthogonal. So it's always subject to this constraint that your weight functions are orthogonal in this sense when you take the integrated product of 0 and 0. So your functions are orthogonal just in the same way in PCA, your basis vectors would be orthogonal. You do need to input what dimensional representation of the data you want to use. The function does output a street plot if you want to use that kind of heuristic measure of how many dimensions to use. But you can also use, so any of the same techniques you might use for PCA, you could also use for this functional PCA to try and determine what the right number of dimensions. Here on the street plot, basically, you really only need, well, I think it's just one dimension that pops up, but I use two because it gives you this nice distinction between the board and really, I think that's the one dimension variation, just or versus and. Or when you look at it with the and baseline, is really high capacity. And when you look at the and baseline, actually tended to be super capacity in these data, but nowhere near as much as or would be when compared to the and baseline. I can go ahead and run that DCA function to give an idea of the full output. Well, a little bit of computation depends, but I didn't do that one. I'm not sure it's one. Oh, there it is. Okay. For the output, you get, these are component scores for each individual in each condition for the two basis functions that are used. So just like we saw in that plot, there's a big difference between the OR task and the AND task. It outputs a step function to represent the mean capacity function across the whole group, as well as the first and second principal function, so the basis function that we're representing it. It also gives you the median RT, so you can choose to, the paper we recommended using a registering the capacity functions by the median response time. The basic idea is that you might have somebody that tends to be a lot slower than the other people, but still be super capacity. So what that means is they're going to have a super capacity function that's just going to be further down the response time scale than the rest of them. So you can choose to register them, kind of subtract out the effect of just slow or fast, and really focus at this capacity question, the question of relative to their baseline, how fast or slow they are. And so you can use registering using mean, or no registering kind of built in. So this one, by default, it does median registration. So then this just also outputs the median RT for each subject. So you get an idea how much of an adjustment there is. Plots. No, plots disappears, but you're welcome to try out the package again and see what the plots look like.
Any other questions?
Well, thank you very much. The R package has my email address in it. I'm always happy to answer questions about the package. I'd also love to have feedback about the usability of the package. So if you're using it and it doesn't make sense, or you do something and it doesn't do what it's supposed to do, please let me know. There is a paper, I think, well, it's easily made available, but there's a paper that describes the kind of baseline functions in the package. That also has some overview information of SF2, that's some data research methods. So that's out there. Again, our citations are all in the package, so it's all out there for you.
Yeah, actually, I'll just ask a question. Even though I should know the answer. Just to actually, given the spirit of communication, show how this could be advantageous and groups like show something yesterday, that we can use one of our capacity measures to deliver near the same result with regard to unlimited capacity within the parallel processing. There's basically a single target self-terminating kind of process, and so we have one target there. then we can also interpret when we started to lose capacity by going to 4 or higher kind of things. And even though we don't have the data there to do a strict architecture test, we can use the inequalities that are part of those programs to ascertain if the loss in capacity was enough to make it a question as to whether we actually switched to a serial process or it was simply limit capacity parallel. So there is a kind of a bound there where you're still getting the savings from having two targets, but or not. So you can hope you answer questions.
Can your package about the capacity estimates can deal with the multiple sources of information, like more than 2 sources of information?
Yeah, so the way it's built is that this RT list, as long as the first one is your everything condition, so if it's an OR task, your redundant target. So if you've got 4 sources of information, all 4 on there, then each one after that is just assumed to be one of the parts. So if you had 10 sources of information, as long as that first one is when all 10 are present, then each of the next ones are each of the individual 10, then it'll go through, it'll calculate the capacity coefficient. The function as it's defined works as the sum of all of the pieces from those individual loop hazards, but has no problem dealing with as many sources as you want to do. The SIC, as it's implemented in the package right now, is just focused on 2 sources. Mario and Jim and Hayo and Young have been looking at generalizations to many more than 2, so as many as you can count. So we hope to build that into the package soon, but it's not there yet. In general, what I like about working on this package is as we continue to push the methodology forward, we can continue to build in stuff. So I mentioned Dan's resilience function. I'm very excited to work with him on building them in there. As we keep building more in, we'll do it.
That's a very beginning question. I tried to download and I never tried R before, but it's curious because I attended other workshops before. So how long it would take for beginners like me to have like a first successful class of that kind of one shape?
3 lines. 3 lines. Maybe not with your own data. So installed packages. SFT, I can't spell install, but yep. I don't think I connected to the internet, so not working. Anyway. Well, see, it works perfectly. Install packages, if that part works. The warning actually doesn't matter. I think it's probably because I'm not online, actually wouldn't install. And because I'm a developer, I have a later version that's online anyway. So I wouldn't want to install it, wipe out my new work. Install packages, data dots. That's enough to get pretty plots. Not quite as good as having your own data in there and building that. It's a good start. And again, like I said, I really am happy to help people walk through this program, so feel free.
Okay, no other questions. We're happy to end the first session, and let's open the floor to Professor Hall.